What's up, gangsters? It's time for a video that's going to be for like 3 of you. And those 3 of you, I hope, will really appreciate this. The rest of you guys will be like, meh, yeah, whatever. Anyhow, quite a few of us have been getting more and more into 3D printing as time has gone by and the technology has improved. And that, of course, has included doing a lot of 3D design using CAD or Blender or ZBrush or whatever to create the parts that we want to print. So one of the things that frustrates me when I watch videos about 3D printing is that they tend to mostly be from guys who are doing like wargaming minis. And 3D printing is ideal, and I'm specifically talking about SLA 3D printing. There are 3 or 4 general categories of 3D printing, but people tend to use, the one term to include all of them. But what I'm specifically talking about is SLA 3D printing, like you get from an Anycubic Photon, an Elegoo Mars, or in the more expensive range, a Form 2. Now, those machines can produce parts that are a lot more ideal for us as scale modelers. But that's the problem with these other videos that I see on YouTube, is that they tend to be more about the wargaming minis, and surface finish is just not as critical because, I mean, obviously you want it to be good for a figure or a bust or a mini or whatever, but because you're dealing with wrinkled clothing and, more organic features, surface finish and resolution just tend not to be as big of a deal as it is with more geometrically shaped hard surface type parts that we as scale modelers tend to deal with. So what I wanted to do, because I've been doing a lot of CAD work and a lot of 3D printing lately, and I've got a bunch of parts just in from 2 different guys using different resins and different layer heights and different settings. And so I kind of wanted to just go through and give you guys a really close look at some of these parts and some of the variations that I'm seeing, and just kind of talk a little bit about how you have to consider your build strategy when you're 3D printing for scale modeling. So anyway, without further lip flapping, let's just get right into it and take a really close look at these parts. Okay, so this is just going to be some running commentary about these parts. I'm not going to get into what they're for or anything like that. Just really focus on the 3D printing aspects of these. Now, just so you're aware up front, all of these that you can see here in the camera frame were printed from an Anycubic Photon, or photons plural, because they actually came from 2 different operators. These up here from one person, and then these down here below from somebody else. This guy is a wizard, very experienced with running his machine, really good at producing really, really tiny parts. But yet what's confusing to me is that when I've been able to talk him out of some of his specific settings, it sounds to me like he's running pretty basic settings. Now, I don't operate a photon myself, so I can't really speak intelligently on that score, but he said pretty normal stuff. I wish I could remember better what he said, but all I can tell you for sure is that these were run at 0.2 millimeter layer or 0.02 millimeter layer thickness, and then these over here were run at 0.05. And this is one of the things that I want to talk about, because you'll see some debate in photon groups and in conversation about whether it's really worthwhile to go any finer in your layer thickness than 0.05 millimeter. And the figure modeling guys, the dudes making miniatures for wargaming and stuff, are the ones that are mostly going to insist that there's no point in going finer than 0.05. And for their stuff, I think they're probably right, because, you know, the wrinkles in clothing and, you know, body features and things like that really lend themselves better than anything to this type of 3D printing, because they just don't tend to show the build layer lines nearly as much. They tend to be more vertical in aspect ratio. You know, a figure, a human figure, for example, is taller than it is wide or you know, front to back, and so they tend to get built vertically, and the layer lines from the build itself just tend to hide themselves pretty well. Same thing with the artifacts from aliasing, which I'll talk about a little bit more in a minute. But what I am finding is, and other guys are finding is to be, I think, definitely true, is that for us scale model guys who are building more mechanical type parts that have flat surfaces and more geometric features, there is definitely an advantage to going to 0.02. And you can really see it here. Okay, so this part, now it's not an apples to apples comparison because the parts are laid down, but let me see if I can find you. Okay, let's see, that is 0.02. That is also, and this is 0.05. Okay, so this is apples to apples pretty much. You'll be able to see. Okay, I also should tell you what resins are involved here. This stuff up here is the anycubic gray. Same with these lighter gray parts here. This is anycubic black, and this over here is elegoo gray. And there's kind of some interesting results here. Okay, but take a look at this part. Okay, this is anycubic gray, and hopefully you're going to be able to see this on camera effectively. Okay, there you go. See the build layer lines on that curved part? Pretty easy to see. And like I said, these are run at a 0.05 layer thickness. Okay, so you can see the layer lines there are pretty distinct in the z-axis. Okay, now look at this one. Okay, this one is a 0.02 part, and take a look at it. Okay, you can see the layer lines are still there, but as you'd expect, they are about half as tall, and there are about twice as many of them. So take another look. Now look, that may not be a huge deal to you. You know, it just kind of depends. It's not like it's horribly difficult to sand those down, because this resin is, you know, it sands really nicely. But again, the less you have to do, the better off you are, because if you've got a part like this one right here, for example, this is in the anycubic gray. Look, you don't want to have to get in there and sand all of those layer lines. Okay, and this is a this is a 0.02 part. So even at that, you may still end up with some layer lines. You know, orientation is really a huge thing here. And the guy that ran this for me and I were talking about whether or not tilting this at an additional angle. So right now it's tilted basically in one direction. It tilted up like that. But if we tilted it also in another direction, it might be a little bit better. I don't know. Haven't decided yet on that part. But that kind of shows you some of the differences in you know what differences in layer thicknesses will get you. Okay, now let me talk a little bit about just some of the differences in the resin itself, because I keep hearing that the Elegoo Gray is the best stuff. That's just the impression that I've gotten, that it's, you know, that it's fantastic, that it's better than the Anycubic stuff, blah blah blah. Well, let's just take a look at some parts. It's in some ways a little bit inconclusive. Okay, if you look at this part right here, okay, this is pretty good. There's not a lot to complain about here. There's not. Okay, this is what I mean by tilting a part at two different angles. Okay, the plane of this thing right here, where we built it flat on this one, it's been tilted in this direction and in this direction, and you can see that there are virtually no, maybe you can see, it's hard for the camera to focus on this gray stuff. You can see that there are virtually no layer lines to speak of. Pretty good. And you can see also what happens. You know, this is also a good study in orientations and how different orientations make a difference. Okay, you can see that we got rid of most of those layer lines on these on the side rail portions of this part. So orientation makes a huge difference. But, all right, as far as the resin goes, okay, the reason that these parts are run in the Anycubic resin is because the guy who runs it says he's tested both, and he definitely prefers the Anycubic Gray. And, you know, when you look at this, I mean, there are no build layer lines going on there that you can see, you know, easily in this part anyway. So, you know, it's just really good, really smooth surface. I'm super impressed. Okay, then you take a look at these. Okay, let's take a look at the tops of these parts right here. Okay, these are 0.05 layer thick. Look at the top of this canister. Okay, you can see the layer lines right there. All right, there's about 4 layers there on that, where that raised section is. And the way that I modeled that is it should be, you know, it's a smooth curve. But obviously there's no way to duplicate a smooth curve. When you're working with flat layers, there's always going to be those artifacts. Okay, now I'm looking for, okay, this is what that part looks like. It's right here. This is what that part looks like. Same resin, but I got to get my lights situated here. Same resin, but I've shot some Mr. Surfacer 1500 on it, but it's at the 0.02 layer thickness, and you can see that it's better there. Okay, but okay, again, same thing, Anycubic Gray. But look, okay, it's interesting that there's a little bit of a weird little divot in the middle of the, or you know, somewhere in the middle of that lid feature. That's not a feature that's supposed to be in there. You can also see, and again, this gets into some orientation stuff, see that there's a couple of little dimples to the left of that lid. Those are supposed to be holes, and they ended up being completely filled in on the parts that were built in their natural orientation, but in parts that were tilted, hopefully you'll see that, parts that were tilted, parts that were tilted, you can see that the holes are still there. So another interesting thing about orientation, you'll hear people say, always build your parts at angles, always build your parts at angles. Well, yes and no. It's like a lot of things. There is no single universal rule. But before I talk about that anymore, let me focus for a second on this other part here. Okay, so look at this one right here. That is Anycubic black at 0.02, and to me it looks just a little bit crisper. Now the reason it's gray is because I shot it with Mr. Surfacer 1500 like all these other parts, but then I put some gray MRP on it so that I'd have a telltale layer when I get to do a little bit of finishing and sanding. And I'll talk about why here in a second. So I honestly am a little bit uncertain as to which one of these resins that I would declare as the best based just on these results. I kind of have to take this guy's word for it because he's run way more parts than I certainly have, who have run none, and the guy who's run these parts. So if he says Anycubic gray is the best, I'm not equipped to disagree with him, and nothing that I've seen here, with this Elegoo stuff would cause me to. I mean, it's good. Look at the resolution on these little parts. Those features are all 0.8 millimeters, I believe, in diameter, and they look good. I mean, they're gonna paint up nice. This part's gonna be black, and I'll do a little dry brushing to call out those fuses sticking out there. But that's gonna look good. Good resolution. Nothing to complain about there. But by the same token, when you look at these parts, the resolution on these is just phenomenal. I mean, it like boggles my mind how crisp the detail is on these. You can see on that Y-shaped part, there's a valve knob in the front of it, and the features on that just came out great. I mean, it's got a hole in the middle of it that you may or may not be able to see that's like 0.5 millimeters, and it's good. And you can see I've got pilot holes in these cylindrical features where I'm going to plug lead wire into to represent the hoses that go there. Came out super crisp. That wall thickness right there is 0.5 millimeter, 20 thousandths of an inch. Super, super good. We'll take another look at some of these here in a second. So again, I guess from this little bit of commentary, if somebody said, what's the best resin? The truth is, I don't know. These all seem to be really good. But certainly, you can't argue that the Anycubic gray is very, very good. I kind of feel like, and I don't know if this is really just true or a perception, I kind of feel like that maybe the Anycubic black is slightly crisper, but again, it's just kind of a perception, and it would be very difficult to really prove that or support that. It may just be a visual thing because it's just the way that black versus gray reflects light. I mean, there they are side by side. I probably should have painted both of those and then taken a look at them before I really tried to form an opinion. But the bottom line is they're both very good. Okay, so enough of that. Let's talk a little bit about supports, because that's a huge issue. And if you're going to get into doing this stuff and you're going to be designing parts like this in Fusion 360 or whatever your CAD package of choice is, you have to be thinking ahead when you're designing these parts. You have to be thinking about how they're going to be assembled into the model. You have to be thinking about which faces are going to be visible, and you have to be thinking about where the supports are going to land. Okay, like this part here, for example. The visibility on this part is going to be from basically how you're looking at it on camera right there. And this bit of it's going to be kind of hidden. So I want these features to be pretty crisp, but you're not really going to have a super good look at this side of it, so that's not quite as important. But I want the top of it, obviously, to be really, really good. So with those, you also have to be thinking about what your capacity is for sanding and filling and doing body work on these little bitty things. I'm not going to be able to sand that effectively. So obviously in this case, I'm going to want the part that's at the 0.02 layer thickness because it's good. I don't have to do any sanding on that. But I am going to have to deal with that mystery divot. That's not going to be too hard though. And I'm obviously going to have to drill those holes that we lost. And I'll talk about why those are gone. I think that is still preferable to the way that this part looks, because with it angled, even though I do retain the holes and I don't have the weird little mystery divot, I do have build layer lines. So it's a trade-off. And with these DLP machines, you're going to be faced with that trade-off no matter which direction you choose to build your parts in. So, positioning and supports are a big deal. But back to the supports thing, you have to really think about where your supports are going to need to be and how it's going to relate to the visibility of the part in the finished model. And this is one reason why I don't like shapeways, because they don't give you any ability to dictate the direction of the parts. They just throw them in their machines, build them however they want to. Okay, but obviously, regardless of whether or not this part is angled or built straight up and down, I want the supports down there underneath because that's going to be invisible. And when you run into it, you get into a part like this, okay, this thing here, for example, it's got hundreds of supports on the bottom of it. And obviously, you don't want to have to deal with any of that being visible. And in this case, it's not, so that's all good. Same thing with this thing right here, all right? It's got all the supports on the underside where no matter what happens, it won't be visible. But what you do have to watch out for are edges, all right? I took one of these parts. I've got another one of these parts right here, and when I took it off of the supports, I was breaking them all out, and I was pretty careful. I used a rotary tool with an abrasive cutoff wheel to chop out, all of these supports around the edges, and I still managed to take a little chip out of one of these edges when I was removing stuff, because this material is relatively brittle, all right? And if you just start going in there and breaking supports off, with brute force or whatever, you will take little chunks out of the edges of things. And I'll show you an example of that right here. So I screwed up and did not tell the guy who was running this little part right here where I wanted the supports, where they were allowable. And you can see that part right here. All right, this is an assembly feature on the back of it that really is just meant to line it up with another mating feature on the part that it attaches to. And so supports would have been okay there, wouldn't have affected it cosmetically. But you can see he built it on the cosmetic with supports on the cosmetic face. And I tried to clean it up, and I did okay. That's just with a file. That's not really trying super hard. Probably would have been okay, but look, when I was clipping the supports off, I clipped, I was being careful, but one of them still broke off the edge right there. So not only does this get into being cognizant of the faces you're going to have supports on, but when you go through your, using your slicer and placing your supports, don't use auto support. You've got to learn to place supports manually and size them appropriately, because here is another great example. Okay, this part, okay, let me see, let's take a look. Okay, this part, you can see that right there at the front of that channel section, it's delaminated, didn't build correctly because the supports failed. All right, same thing on this side. It's supposed to be square, but it's not because the supports failed. All right, and he had reduced the support diameter down to a really fine amount, which is great as long as you've still got enough. So he ended up having to rerun those with a little heavier support. You can see on this one, the edge of that rail is square like it's supposed to be. But when I go to remove that, I'm going to have to be very careful not to let that chip like I did on one of the other, on that part that I showed you, because again, it's just brittle and you're dealing with very fine features right there. So this brings up another point about supports. A lot of people who will run parts for you are going to clip the supports off before they do the final cure. So basically they take them out of the machine, the material is still a bit soft, they'll remove the supports, then cure them. I don't really like that. I, in fact, ask anybody who's making parts for me to let me remove the supports, because I know best what I want, and I don't have to worry, about somebody not knowing what's really an important feature, what's going to be visible or not visible, and if removing the supports, is a problem, then it's on me. But that's also why I recommend, if you can afford it, because look, if you're paying somebody to run parts, this can get expensive. Get yourself an extra set so that you've got practice parts and you can see what's up before you are really committed and you run something that you paid a lot of money for. Okay, so with supports, all right, so I think that's all that's worth saying there. Let's talk about orientation a little bit more. This I've already talked a little bit about. This is a really good example of how orientation makes such a huge difference in the quality of the parts. I kind of wanted this thing right here built flat because that face of it is planar, and you obviously, if you build it flat, you get a perfect surface on that particular thing. But obviously those curved arms, not so much. You can see the layer lines there. And obviously building the parts flat would have been great for those rails, but only if all the supports worked. Building it at an angle solves a lot of those problems. So in that case, going against your intuition about the natural orientation of the part is the right thing to do, because if everything is working the way it's supposed to, even at an angle, you're going to get really good surface definition. But I do have some build layer lines going on this face of this arm. Not too big of a deal. That's easy to get to. I can sand that off. So if you're working with somebody who will communicate with you and let you kind of tell them what's important, that's the ideal thing, because you can let them know, hey, look, I can tolerate a little bit of surface roughness on this face and this face because I can get to it with a sander. This other face, there's no way I can. So, you just really have to be able to collaborate. Okay, now let's take, I showed you already some differences in this part, built natural versus angled. Okay, look at these little cylinders here, okay? This is where the rule about always building at an angle just falls apart. Okay, these little cylinders right here, if you can kind of tell, I don't know if the camera will focus, you can see that they just really don't look all that great. They just didn't really build that good, because it's extrapolating a cylinder from a series of oval-shaped slices. And there's just always that danger of it not really working out right. If you can stick to a pure cylinder the whole way, you're going to get a better part with better definition. And you can see that there, where these are built in their natural orientation, where they stand up, that the quality is better. So again, that alleged rule of building everything at an angle, yeah, again, it just depends on the part. And that's a lot more true with mechanical type parts than it is with stuff that's got a more organic shape. Okay, so talked about materials, talked about supports, talked about orientation. Here's a good example of where building the part flat is absolutely the right thing to do. That surface finish looks great, and these parts are flexible and they're going to get glued to something else, so they don't have to be super perfectly flat, and the back face that the little bitty supports on are a non-issue. And look, these were built at 0.05. So again, just to reiterate, when it comes to positioning, don't buy into any rules that tell you absolutely that one position is better than another. Here's another good example, okay? This part built flat, which kind of made sense because this thing here, this disc, is planar. Well, it didn't really work out so good because you can see it warped badly. That obviously is not going to work at all. All right, this part was built at a 45-degree angle. That's pretty good, but you can see with some primer on it that it's got some artifacts, some layer lines. This version of it, same layer thickness, both of these are at 0.02. This one has a lot less in the way of layer lines, but if you look at it really close, okay, this is going to be kind of hard to tell on this part that's not primed, but if you look down next to those gizmos, whatever they are, you can see that there's a groove that runs all the way around them, and then there's an annular groove between the sections, the cylindrical sections. I put that in there in the CAD because there's got to be a color separation there between parts that are gray and metallic silver and just pure aluminum, and I'm going to want to run a wash in there, and that groove is there to hold the wash, just like a panel line is on an injection molded part. And you can see that my groove, for whatever reason, looks better, I believe, on this part built at 45 degrees than it does on this part that was only built at 30. I mean, it's pretty tough to tell, but I do think that there's a little bit of a difference. Again, it's really minor. One thing I can tell you is that there's supposed to be a split line between the top and bottom half of that little fixture piece that you can see there. It's actually called a Lord mount. Is what that is. It's what holds the radial engine to the motor mount, or to the engine mount frame. Anyway, there's supposed to be a split line there because that's a cap that's held on there with those two bolts that you see from that direction, and it just disappeared completely. And I think that in CAD it's 0.1 millimeter. It's just too small. I think what I'm learning is that kind of a rule of thumb on feature size for parts is when you start getting below 0.2 millimeter, you're probably going to lose. You're probably going to lose your feature definition, and you can see a little bit of that here. So this is the next thing I'll talk about is knowing when you're working in CAD what you can realistically get away with. Like look at these parts right here. Okay. Again, I've shot primer on these because that's really the only way that you can really see what's going on. Okay, those little screws, screw heads, whatever you want to call them, they're basically just little bitty cylinders. Those are 0.3 millimeters by 0.1 millimeters tall, and they came out pretty good on the angled version of the part. Same thing over here, 0.3 by 0.1. That's kind of what I standardized those little features at. They look pretty good. But when you flip it around, okay, and you start talking about raised rivets versus recessed rivets, okay? So like all these in here, same thing. These are 0.3 by 0.1. And you always want to keep about a rivet's diameter distance between the center of the rivet and the edge of something, because especially if it's an innie as opposed to an outie, if it's any closer than that to the edge, you're going to lose it. Okay, and look, these rivets that run along the edge of this thing, and I'm not sure if it's going to actually show them, are a good example. Let me find a part that's got those. Okay, here we go. On this face of this box right here, okay, those are all supposed to be inset rivets that are also 0.3 by 0.1 deep. And you can see that they really just are not that well defined. And interesting, okay, when we built the part in its natural orientation, we lost them completely. They're just, some of those holes are just barely visible there. You can kind of almost see the rivets. I mean, I basically lost them. So what's happened there? Why did we lose those features? So here's a little bit of 3D printing 101. Okay, so what happens with this type of machine? All right, and for those of you that are kind of new to this, all of these can be classified as SLA parts, and SLA stands for stereolithography apparatus. And this is the original type of 3D printing. And basically what's happening is this is a liquid resin that reacts to light of a certain wavelength, and that's what causes it to harden. It's very similar to UV glue, like Bondic, for example. And in fact, you can make repairs to parts like this. If you've got, like I have that little divot that I need to fill on some of these parts. If I had a bottle of resin, I could just take a little bit of liquid resin out, fill the defect, and then use one of my UV LED flashlights that I use for UV curing glue to harden it, and it would be fine. Okay, but what happens is that in these machines, the original SLA machines, parts like this one, for example, this is run on a Form 2. Okay, the difference between a Form 2 and a photon is that the Form 2 uses a laser to do the curing of the resin. So what happens is, let's say that you've got a layer that looks like this, square with a hole in the middle of it. Okay, so what happens is the laser comes along and it draws the outline like this, and then comes back and scans across there to fill it in. Okay, so it's like basically like just exactly like you would draw it with your with your pen. Okay, these parts, anything made on the less expensive machines that cost, like the Anycubic Photon is like a $300 machine. The Form 2 is a $5,000 machine, which ironically I'm finding is not as good at making these really finely detailed small parts. But the way that the Anycubic works is it's basically going to create a mask. Okay, and if you have this same cross section, square with a hole in it, what it's going to do is it's going to make a mask using pixels on an LED screen. And so you can imagine that the pixels are doing this sort of thing to approximate what each one of these curves looks like. If you got nothing but straight lines, you're golden because pixels are square. So you got, you have a perfect match. But when you have a curved line, obviously that screws up. And basically, this is exactly analogous to the difference between vector graphics in Adobe Illustrator and raster graphics in Photoshop. Raster graphics are made up of all these little squares. So that's also why this is one of those trade-offs. In a machine where you're running a laser, you don't get artifacts in the XY plane like you do with a machine that's using the screen mask technology. And you can see that, okay? That's why, like on the side of this part, you can't really see it all that well there. Right, here we go. Right here, okay, on the side of that tank right there, you can see that vertical defect that runs in the Z-axis, okay? That's from the jaggies caused by the pixels in the mask. And that's where anti-aliasing comes in. So just like with graphics, you can turn on anti-aliasing to where it does some stuff in its little computer brain to smooth out the jaggies, but that comes at the cost of sometimes giving you less detail resolution. So again, with the trade-offs. Now back to why did I lose the holes in some of these features. Okay, so here's where we get into some of the chemistry of or physics or whatever of the resins. All right, if you're using a laser machine, what happens is the laser shines down and it creates a spot. And the spot gets traced all the way around this outline. So imagine that this is the laser spot, and the exact center of the laser is this circle. But what happens is that the resin does not cure exactly with that same diameter of spot. There's a little bit of bloom. You get a little bit of overspray, if you want to call it that, all the way around the outside of that also gets cured. So basically what happens is that this feature, okay, could end up being a little bit larger because of that overcure than it really is supposed to be. Now, back in the day when I was running machines like this 25 years ago, it was a different type of machine, but it had a setting in it called beam offset, where basically you scoot the beam over a little bit to account for the bloom around the laser spot. And again, it's not ever going to be perfect, but that's what you kind of have to account for. Same thing happens with the DLP type machine. The mask is only going to basically can only be so perfect in its ability to block the light that's shining through and doing the cure. So what you might have, if this feature right here is a hole, as you've defined it in CAD, what's actually going to happen is you're going to get a little bit of overcure, and you end up with a hole that's a little bit smaller. And that's why I lost the holes on the tops of these things, because there's resin just sitting in there, and the bloom causes that to cure, and so it just basically fills in. So what I need to do is allow for that in CAD. All right, and here's a good example of how that kind of works. If you look at these parts right here, these are these have both an innie and an outie, and they're both supposed to be 0.7 millimeters in diameter. But you can visibly see that the hole is slightly smaller. So what you have to do to account for that, if that's really important, is in CAD, you have to just sort of make a judgment call as to how much you should oversize that feature beyond what you want it to be. If it's supposed to be 0.1, you're probably going to end up needing to make it something like 0.3. That may not even be enough. You may have to make it like 0.4 or 0.5. Point being is you're just going to have to figure out from experience how to make adjustments on those kind of features to account for the tolerances. And that's where you get into some real mechanical engineering, because tolerances are the bane of a mechanical engineer's existence. And you can see it like parts like this, okay? This part right here has that little assembly feature on the back of it. That is supposed to fit on one of these ribs right here. These ribs are nominally 0.8 millimeters thick and I made the gap between those two nubs right there 1 millimeter. I figured 0.2 millimeter should be enough slop to make it where the part would fit. Well, it doesn't. It's too tight. And it's because if I measure the thickness of this rib, you can see it actually came out to be 0.95. So it's like a line-to-line fit right there. So you kind of have to figure out for yourself what the size of all of these features is actually supposed to be, and how much you need to allow for them to, take up the tolerances in your assembly. And that's where running your own parts, as opposed to having somebody else do it, is definitely going to be an advantage. But, if you're like me and you don't have space and don't really want to deal with, storing your resins and all that stuff, then you don't really have any choice. You got to pay somebody to run parts for you. So you just have to sort of learn the engineering of it as you go, and you may, end up spending some money to learn those lessons. So anyway, I think that's kind of I think a good kind of summary of how you can evaluate parts and how you have to think about 3D printed parts when you're designing them in CAD, and what some of the issues are that you can run into between the resin you use, the orientation of the parts, the way that the supports are going to get put on there, and the way that your tolerances are going to be affected by the process itself. Okay, so there you go. As I said, exhausting, tedious, detailed, nerdy, whatever you want to call it. But I think this is important stuff if you really want to get good quality 3D prints. And again, the demands of scale modeling are different than what a lot of people are doing with these machines. So I feel like this kind of fills a little bit of a hole as far as information goes. Again, I'm not running a printer myself. I'm farming it out right now because I just don't have the time or the space to deal with owning one of my own. So I'm looking at it a little bit differently, and I'm sure that there are some considerations from the operator side that I would feel differently about if I actually had a machine sitting here in front of me. But as a user, these are the kind of things that I see, and as a designer, these are the kind of things that I feel like you have to take into account. One other point that I wanted to make on the user side is leave your parts attached to the supports as long as possible. I know I mentioned in there that people tend to clip the supports off before they cure the parts, and there's reasons for that. But I say to leave them on there for scale modeling purposes, for the same reason that I advocate leaving parts on the sprue as long as possible, because this gives you something to hold on to while you're doing your cleanup operations. Like, I generally don't expect holes to be the exact size. I expect that I'm going to have to clean them out with a drill. So again, this is a very handy way to be able to hold on to that while I do those kind of operations. Any kind of finishing work, painting, whatever, it's all easier to do when you've got that handle on there. So anyway, I think that's about enough of that. Like I said, I hope you guys found this useful if you're already doing some 3D printing or are looking to get into it. All right? As always, I appreciate you guys watching. Much love.